Let's wait a couple of minutes for everybody to come in. Recording. Hello again, everybody. Let's start our discussion today and share my screen. And as we advertised last time, we are going to spend a little bit of time today on what we call discrete time systems. These are systems which we understand, we being either the computer or humans or both, understand by looking at specific points in time, distinct points in time, or discrete time in general. And the reason why this is worth exploring is because that's the natural setting in which computers work. With computers, of course, you all are familiar with the basic ideas about clock that sends commands to a processor and so forth. And these clocks run in gigahertz these days, right? Your watch or your cell phone or your laptop or tablet have megahertz, gigahertz processors. So they are very, very, very fast. Now, that's not what we are looking at right now when we deal with process control systems. We are looking at signals that are sampled in time at distinct points, and that's what the discussion in this chapter is, and it's another PDF that I already mentioned. It's the discrete time systems PDF that we have on Canvas, and that's what we're going to discuss today. So, references on that. Any good textbook, undergraduate textbook, I've already mentioned two in the notes by Astrom and Wittenmark. It's in its third edition. Actually, I like the first edition more because it had some minor omissions, but it was more succinct and easier to understand and follow. And from a viewpoint of intuition, it was still just as good as the third edition. Astrom was saying that his colleagues were complaining his text we didn't have enough theorems there, so he put some more theorems to make it look more scientific. But nevertheless, it's an excellent textbook. At the undergraduate textbook, this is covered also in standard textbooks like Stephanopoulos or Seaborg, Edgar, and others, of which we have mentioned several times. It's all covered there. The notes are self-contained. We should be able to understand all the tools that we need by simply looking at the notes, right? in somewhat telegraphic form, but nevertheless, they're complete. So it's interesting to note that here we are talking about signals which are continuous in time. This is my signal as a function of time, and this is time. But the thing is that the computer selects samples of this signal by picking values of that signal at distinct points in time. How this is done is another subject, but it is routine today. All industrial systems, well, most industrial systems today that deal with data acquisition have this capability after perhaps an analog sensor that creates a voltage or a current or something which continues, and then that is immediately converted through an analog to digital converter from analog to digital, and from this signal you get these points here that I already mentioned. Actually, I should draw it like this for the two to match. The computer then may do some calculations, and then if you want to send a command to a pump or a valve or a compressor or something, well, it has to be a continuous signal. The equipment needs to know what the input is at all times. So when the computer has these values determined, essentially what goes from a digital to analog converter to the process is not these values, but rather a staircase pattern like this, which means essentially that the signal, the continuous signal that goes to the process is maintained constant in between the sampling points. That technology is, by engineering standards, more recent. Control systems have been around for a couple of centuries. Digital control systems have been around for about half a century, I would say. And of course, these days, everything is digital. I have in the notes a brief history of those systems. In those points, which you can read on your own, it is of interest, this is on page 4 of the notes. It is of interest to notice an event in 1959. 1959, we had the first digital process control system at a Texaco refinery. Texaco was bought by Chevron a few years back, so it's Chevron today. But Texaco was at the time an independent company, and they had a refinery at Port Arthur, not far from here, going east, which is still in operation, by the way. Well, the control system is not in operation because it is primitive by today's standards. A thank you or happy birthday card that you send in the mail today, when it sings a nice jingle, it probably has more memory and processing capability than that control system had. But it did a marvelous job. And remember the hierarchy of control systems that we have. We have mentioned this several times. I draw it very quickly because it's important, so it's good to be reminded of that. So I have here the process. Here we have the direct PID level, and here we have the APC level. And those communicate, and there is feedback. Actually, there may be feedback directly from this, as is in all the other levels. Well, that 1959 system, which was a Remo Wooldridge computer. Remo Wooldridge are the R&W, a company called TRW, which is one of the big three that has your credit card information and everything, in case you get a credit report when you want to buy a car, a house, or any of those things. So that computer had a tiny memory in the, I think it was 64 kilobytes. That's 1,000 bytes, mega, not gigabytes. Yet it could provide good control at that level. It was actually at the level that we call perhaps today SCADA, or just SCADA is supervisory control and data acquisition system, or just supervisory. And it did essentially some sort of real-time optimization. So it was model predictive control and RTO, very little dynamics. So it worked. It provided optimal settings to the PID controllers, which were all continuous at the time, so that they could control the plant. In the 70s, we had microprocessor control. And of course, the big boom came along in the 80s with the advent of the PC and chips, CPUs that were powerful enough to do lots of calculations without having to resort to a mainframe. The old computers actually had to resort to a mainframe to do the calculations. That system that we mentioned in Port Arthur used a dedicated computer. Actually, earlier systems, even before that, would send commands to a central computer, perhaps hundreds, maybe thousands of miles away, for the calculations to be done, and then the results to be sent back for operators then to dial in the new results. We've come a long way where everything is integrated. Yet, the theory and the fundamentals remain the same. There are certain capabilities and certain limitations that remain valid, and it is these that we're going to cover, because those are going to remain relevant for a long time to come, even though the technology is going to be so much better. I have on page 4 also a historical paper Note that this was published in 1978, and actually it was 1976 when that paper was first presented at the conference. And it has in its title the terms model predictive heuristic control. So what the engineers did was come up with a nice technique that would allow them to control systems with multiple variables. And at the same time, they would have to keep all variables that were constrained within their constraints without violating these constraints. That technology solved a very difficult problem in a single solution, a powerful solution, which to this day remains the de facto standard of advanced control. It started in process control and it has migrated now to other control systems, from anti-lock brakes to buildings control to flight control and so forth. Also very interesting is the fact that, as you can read in the note, it says model predictive. So I'll write it here, model predictive heuristic control. The term heuristic is deliberately used by the authors because indeed this didn't look like anything they had seen before. It looked very, very different from everything else that existed out there. Actually, it turned out that there was already plenty of theory beyond that. There was theory that was developed in aerospace, also in other control systems, which was relevant to that idea. So there are two lessons here. One lesson is give clever engineers enough time, they'll come up with ingenious solutions, even heuristically. But also there is another lesson. If clever engineers can find a solution heuristically, after spending a lot of time, maybe it's also a good idea for clever engineers to know a little bit of theory, which may not be immediately applicable to what they're doing, but maybe that theory is relevant to what they're doing, so they can take it, modify it, and use it even better. This is not the only time when this has happened. Okay? It has happened numerous other occasions. One well-known case was the discovery of wavelets. You're all familiar with how Fourier transforms express a signal as a sum of sines and cosines. We covered that already, right? Well, wavelets express a signal not as a sum of waves, but as a sum of small waves that are chirps like that. So you have chirps like that of various frequencies. You assemble them, you put lots and lots and lots of those together, which you translate in time, and boom, you have a very good representation of a signal. That was discovered, again, heuristically by a very clever engineer who was working on seismic data processing in oil and gas exploration. It turned out there was a beautiful mathematical theory, which was further developed, of course, after this realization. All the links between existing solutions and this idea and application were put together. And today we have a very nice tool, which is used sometimes by chemists as well, in signal processing. So with that historical review, again, I would say that today, practically control systems from sophisticated MPC systems or RTO, real-time optimization or model predictive control systems, or PID controllers, those are all digitals. Some buzzwords that you may hear is SCADA, that is just an acronym that used to stand for Supervisory Control and Data Acquisition System. Those were of a certain kind. Then over time, those became more and more and more and more and more powerful that ended up doing all kinds of things beyond that. Then there is also PLC. Anybody has worked with a PLC or seen a PLC? So this stands for Programmable Logic Controllers. In a nutshell, those were controllers like the one you have in your washing machine, which says you soak the laundry for 12 minutes, and then you wash for 20, and then you spin for 3, and blah, blah, blah. There is an electronic circuit there that does all these things sequentially. So this is programmable, and there is logic. Logic may be time-driven or event-driven or a combination of those. All those were done with electromechanical equipment way back when. These days, it's all computerized. So it's very, very easy to use, to program, and the capabilities now are the capabilities of a computer. So they are still called PLCs, but essentially they are powerful computers. And they include all the capabilities that you can find in SCADA, and of course, some of these capabilities, and definitely some of these capabilities of process controllers. You can easily put a PI, or actually multiple PIDs in a PLC system. To understand how these systems work, as I have already mentioned several times, and I emphasize again in section 3 of the notes on page 5, we need 4 things. First and foremost, process knowledge. We need to understand the system. Without it, no luck. How we take measurements. And we will see here that actually how we take measurements is not as trivial as with continuous systems, because with continuous systems, you have a sensor, you stick it there, it provides a voltage, let's say, in real time, done. Okay, you have your measurement, so you just pick it up and you move on. Here they have other questions such as how frequently do we sample? The computer can execute things in gigahertz, but I'm not going to sample at gigahertz. So how frequently? We'll see this in a second. Then measurement technology. Of course, now we have smart sensors that remove noise automatically. They condition the signal. They can smooth it out and so forth. Computer technology, we need to understand a few things about that. And finally, control theory. So we will cover all of these, but in increasing order. So this is not a process knowledge course. So we'll deal with processes, but mostly with control theory and the other two, computer technology. So let's try to understand, first of all, how a digital feedback loop works. And this is a single loop with a single controller and a single process, a single input, single output. So here I have the process. And here I have the controller. Now, the process generates an output. Again, these are block diagrams. There is no pipe, no metal, no fluids flowing through, no nothing. These are all signals I'm drawing at this point. Okay, so there is a signal here, which is something like this, a continuous signal over time. That signal is sampled. So you may call this an analog to digital converter, AD or A to D, or sampler. All of these names are used. And from this signal that I indicated here to the right, this A to D converter creates another signal, which is like this. So it creates values of this signal at distinct points in time. So this is time again, but you have T0, T1, T2, Tk, etc. All these time points. And each pair rather, is separated by a certain time interval. You can call it delta T or T capital. We'll see what the significance of that is in a second. This is sent to a controller. The controller is essentially a computer. It's a digital device. From a simple to a sophisticated computer, it's a computer. So here we need to give some commands. So we need to provide external goals. For example, we can provide set points. We can provide constraints. Now that we have a computer to our disposal, we can introduce a lot more logic to the system. It's not like the old days of electromechanical equipment to select between two values, the larger one and so forth. Now we can do sophisticated calculations very, very easily. So the controller, of course, understands this signal here in discrete time. So at every point in time, as instructed, the controller takes this value, and assuming it can do calculations, number crunching blindingly fast, it immediately produces some commands over time like this. And this is the signal that is produced. And of course, these commands must be converted to an actual signal that will go to the process at all times. So this will be something like that. And this is sometimes called the digital to analog converter, or DA converter, or the zero order hold. Zero order hold. Why zero order hold? So this is zero order hold, this is computer. Because if we have a system that starts from this value and it is, let's say, first order, well, it moves somewhere like this, okay? If we have a zero order system, it is zero order, it holds its initial value, it stays like that. No dynamics, no nothing. It is what its initial value is. So if the computer said, let me magnify this. So if the computer sent this signal, then I'm going to put lots of these, so these values. The zero order hold says at this point, which is something, let's say tk, I'll hold this value, and now I have this value. I'll hold it there at point tk plus 1. I'll hold this value at tk plus 2, and something like this, tk plus 3. And I'll keep going like this forever and ever. So this staircase pattern is what is fed to the process, and the process experiences that. So let me draw my signal also to complete my description here. So what goes there is something like this. Let me highlight all of my signals in the loop. So this is the continuous output, the discretized measurement that goes to the controller, the discretized output of the controller, and then the continuous input to the process. So this might be called our input Y, this might be our input U, and this closes the loop, the feedback loop. So this is my feedback loop. And of course, there are disturbances also to the process. All the nice things that we learn about external signals to the loop are important here. Now, immediately, there are questions that we would like to raise here and find some reasonably satisfying answers without getting into too much detail. One can actually go to deep analysis here, but thankfully, chemical engineering systems are not extremely fast, so we won't need to go to all that deep analysis, but nevertheless, because we collect lots of data, how fast we are sampling and what do we do with the measurements and all that are things of interest. So we're going to look at things like this, for example. So delta T is what? How should we sample here? Or the controller takes inputs from measurements. It takes set points and constraints, which are in discrete form. This has been done here already. So here, if you have a human, there is always something that translates these in a digital form. Typically, actually, this is built into the controller. So it's just one box. You see one box there. So what is that box? How does it do number crunching to produce these things? And finally, if I am to design this box here, what can I expect about how this and that, those external signals, affect the outputs of my process, like this and this? How do these how does the design of my controller affect the response that I get in my closed loop? So let's start looking at those as I have it in the notes. So first thing which we check in section 5 in the notes, which is page 7, is sampling of continuous time signals. Well, if I have continuous times signals, then how frequently I sample makes a difference. And first of all, let's think about what issues are there. Why don't I just sample very, very fast? If my computer can process data at gigahertz speed, well, okay, maybe I can sample at kilohertz speed, let's say, for my process, right? My computer it's 6 orders of magnitude below a gigahertz. So my computer would be able to process these measurements and wouldn't have a problem. Just heuristically thinking, without thinking about anything else. Would that be a good idea practically as an engineer if you have, let's say, a heater, it has a temperature which is continuous, and you sample that temperature with kilohertz frequency? Well, you all know what a hertz is, by the way, right? It's cycles per second. So I take kilohertz speed means I take 1,000 cycles, 1,000 measurements per second. I would take these measurements, put them in an Excel sheet, and I would go. Any practical issues with this?
You might not be able to change. Telling it to go.
Yeah, so you're saying kilohertz is probably excessively high, right?
Yes.
Temperature in a heater doesn't change that fast. And there you go. And we'll do this quantitatively as well. That's an excellent point. So I don't need to do it that fast. And in fact, if I did it that fast and I put all the measurements in an Excel sheet, what do you think would happen to my Excel sheet? Well, it would be really wrong very quickly. It would overflow, right? So there are issues there. How do I store these data? How do I process these data? And so forth. Therefore, there's an incentive, even though my electronics are gigahertz speeds, my actual process doesn't have this kind of frequency at a billion measurements per second. I can probably look at the temperature and measure it every second or every minute, I would say, and still have a pretty good feel for how it changes, right? So this is one issue, namely, if we just look at what the electronics can do, yeah, the electronics can sample things extremely fast, but we don't need all that speed. And actually, we cannot handle all that speed. It becomes very unmanageable very quickly. On the other hand, it is possible that if I don't sample fast enough, I may miss some important features of my signal, right? Let's say example 1 on page 5 that discusses exactly that. Let's take the following simple situation. So the purpose of this example is to show what happens if I don't sample fast enough. We'll show this example with just a sinusoidal signal. And then we'll see a more specific example with an actual signal, presumably coming from a heat exchanger, so we can see what the issues are there. So our sine is this. I'll just put, this is 2 pi, right, for a period. So this is 4 pi. This is 6 pi, 8 pi, and so forth. So middle point here. So my sinusoid is like correct? Okay. Now, 2 pi is 6.3, right? And 4 pi is 12.6. And this 6 pi is 18.9. And 8 pi is 25.2. Is my algebra correct? Okay. And let's say that we sample every 6 time units. So delta t is 6 time units. If time is in seconds, it's 6 seconds. If time is minutes, 6 minutes, and so forth. Well, if I sample every 6 minutes, so this 2 pi, let me try to make it a little cleaner. So here, so 6 is here somewhere, right? Agree? And then I have 12.6. So 12 is here, so this is 6. And this is 12. And I have 18 here. Something, and then 24 here somewhere. Right? So what do you observe? If I sample this sinusoid every 6 time units, is this a good idea? Not really, because if I look at these points, you see they follow this pattern. If I continue, you will see that it's this pattern, which is what I'm showing in more detail in the figure of example 1, which shows the different patterns that one can get. In fact, let me open that file. Give me just 1 second. So let's copy this to the notes so we can refer to this directly and try to understand what's going on. So I'm referring to this figure here. Okay. I can stick in my notes here now, so we can refer to this a little more quantitatively. So what I drew up here in red and blue is light blue is indicated here more accurately using the actual sampling of the sinusoidal signal. And you see here also that if I sample every 2 time units, well, you may be misled into thinking that this actually is indicating that I get three signals like this, right? But in reality, if you just look at these samples, theory says that you can do a decent reconstruction of the original signal. It's not too bad. And of course, much better is to sample not every 2 time units, and certainly not every 6 units, but definitely every 0.5, right? And of course, this raises that question. So how frequently do you sample? How did you know that 6 is bad, 2 is good, and so forth? This was solved a number of times. Like all great discoveries, it deserves to be discovered several times. So Nyquist in the 20s, an engineer at Bell Labs figured out that when you sample a signal, well, the signal has what we call a Fourier spectrum. That's a fancy name that says if I have a signal, we did that last time, so let me repeat qualitatively what that means. Let's keep it at a finite interval from here to here, to L. If I have this signal, we explained in a previous figure that I can express this signal as a sum of sines and cosines. So this is one sine, this is a sine of twice the frequency, and then I can get a sine of 3 times the frequency, and pretty quickly I get here a lot of clutter. And the idea is that by looking at the coefficients of the corresponding sines and cosines, so I have here the sines, I have the cosines here, same story, so you have something like this. You keep going, this is time, this is time. By looking at the coefficients, you can figure out what's going to the signal, but there is an important notion that says if you have here frequency of the sines, so this is sine omega t, and this is cosine omega t. The amplitude, so our signal f of t, we explained its sum of ak cosine omega kt plus bk sine omega kt. K goes from 0 to infinity. Okay, oops. This summation. The AK and the BK coefficients, the magnitude of these coefficients goes down to 0 very quickly. Okay, for all signals. So this will be 0. The largest frequency where these signals, the sines and cosines have a sensible amplitude larger than 0, is what we say is the largest frequency of our signal. Beyond that, the signal does not contain any frequencies. Then Nyquist, in his famous theorem, said something very, very simple. If you want from the if you want from the sample data to be able to reconstruct the original signal, to do something like this, the sampling period or the sampling frequency, let's put it like this, the sampling frequency must be greater than twice the largest frequency of your signal. Or in other words, the sampling period must be less than 1/2 of the period corresponding to the largest frequency, to the shortest period of your signal. In fact, because these things are so important, if you take that equation and inequality rather, you write it as omega s over 2 greater than omega 0. This aptly is called the Nyquist frequency. So the Nyquist criterion says the Nyquist frequency must be greater than the largest frequency in the signal that you are dealing with. We'll see in a second that this gives us a nice rule of thumb that says if you have, for example, a first order process plus time delay, if the time constant of your process is, say, of a certain magnitude, you need to sample at least 10 times per time constant, or the sampling period should be, say, roughly 1/10 or less of the time constant of your process. It's a practical rule of thumb that is followed in industry quite extensively. We'll explain why. Before we go to that, let's make sure we follow here what's going on. So let's make sure we understand all the symbols and all these things that we mentioned here with formulas. These are well-known symbols and formulas, but let's make sure we don't slip up anywhere. So let me do it like this here. So sinusoidal signals, let's take this that we have up here. So here we have a sinusoidal signal. Let me magnify it like this. So 2 pi is my period. The period of my signal is 2 pi. This sinusoidal signal, f of t versus t, has just one frequency, no more than that. So it has only one coefficient, bk, which is 1, let's say. Good. So if this is a signal that has a period of 2 pi, what is the corresponding frequency? Omega 0. in radians per unit time. As always, it's 2 pi over t, right? Or t0, which is how much in this case? One, yeah. Because this signal that I just drew here, what is the signal again? What function? Yeah, sine t. Okay, this is sine of 1t, basically. And so sine t has a frequency of 1, and it has a period of 2 pi. Other signals that are a sine of 10t have a frequency of 10 radians per time unit, and a period which is 2 pi over 10. Okay, very simple. And Nyquist's theorem says that in order to be able to reconstruct the original signal from its samples without introducing artifacts, then I need to sample more frequently than twice per period. Okay, so if my period is 2 pi, which is 6.2, that means I should be sampling at least twice per period, preferably more. Okay, so twice per period means my sampling period should be, the sampling period should be below this. So the sampling period should be below that line, right? This should be my sampling period, because this is the middle point, this is half, this is T0 halves. And as my theorem says, I should be below T0 halves. Or the frequency, the sampling frequency, so to speak, should be higher than twice the basic frequency. So more than twice per period. So let's look at what we got here again to make sure we follow what's going on. So here, what was the sampling period again? 6. Okay, 6 less than half the signal's period T0? No, what is the signal's period again? 6.2, yes. Okay, so 6 is not less than 6.2. Half the period is here, 3.1. 6 is here. So the sampling period that I considered here is not good. And that's why it creates this artificial sign, which we'll explain in a second how to calculate it. But this is called an alias signal. So what happens if we don't have these, either one of the two satisfied, or this, of the three? If we don't have these, if this is not satisfied, then we have what is called aliasing. Aliasing means the points that we sample create artificial frequencies. This creates here an artificial signal. This is not the real period of our signal. This is an alias signal, and we'll give a nice example in a second. Before we do this, let's complete this discussion. So Nyquist says if you sample at least twice per the sampling frequency, or more frequently than twice per period, you will be able to reconstruct the original signal, the continuous signal. In fact, Shannon, years later, developed an entire theory which includes that reconstruction formula, how from sample points of your function at time tk, if I have these sample points, how can I reconstruct my original signal, f of t? Well, I can reconstruct this signal from the sample points. So these points again are T1, T2, T3. So these are points here that go to minus infinity and plus infinity in time. Okay, I assume a signal that is not limited. There are other versions, but let's keep it simple. So I take these samples, multiply them by something, and then sum this for k going from minus infinity to plus infinity, and bingo, I have my signal. That's a theorem that is perhaps best known as Shannon's theorem. It was known to Nyquist and others actually at the time, but Shannon created a whole theory based on these ideas. And what you have to multiply by actually is this interesting expression, say omega sample t minus tk over 2 divide by omega sampling t minus tk over 2. This is my continuous signal. Okay, so my continuous signal f of t is this function of time. I can reconstruct it exactly continuously. The caveat is that I must satisfy the Nyquist frequency. So if I have this or that satisfied, then I have this beautiful expression. If not, I don't. If not, I create what are known as alias frequencies. Now, in the notes, for those who are more knowledgeable about these ideas, I include theorem 1 that Shannon proved, where this formula is proven. And there is actually a theorem that explains how aliasing comes about. Aliasing is essentially the idea that the discrete and continuous Fourier transforms don't match if I don't sample fast enough. But this gets into hairy math, and that's not my objective here. I don't want to confuse you. What is simple to follow, though, is what I have in corollary 1, which is on page 11, which is actually very nice and simple. And actually, we can do calculations with that. Let's see that nice theorem. What does this theorem say? It says, if I don't sample frequently enough, I run into problems of this kind. Well, what frequencies will I create if I have a signal that has many frequencies and I don't sample frequently enough? The theorem, the corollary, actually, corollary 1 on page 11 says the following. If I sample a function f of t, and I take samples at points tk, which are equidistant, uniformly spaced, as I am showing here. This is tk, and this is f at tk. If I have these points, and if my function f of t contains frequencies, let's call them nu, which are larger than the Nyquist frequency, which is defined again how? It's my sampling frequency divided by 2, which is defined how again? 2 pi over sampling a period divided by 2. The 2 cancels. So this is pi over tau sample, pi over t sampling. This is an important number. So if my signal contains sines and cosines at frequencies that are higher than the frequency, the Nyquist frequency, then I will create alias frequencies. And those alias frequencies actually will be as follows. Those alias frequencies will be of the form k omega s plus or minus omega, where this omega a will be all the numbers I can fit, all the frequencies I can fit from upstairs, from this expression, where omega a must be between 0 and omega n. So if my signal contains any of these frequencies, each one of these is going to create an alias frequency. This is why you have example 2 explains that if you have movies and you have a camera that is taking, say, a car chase, and you have wheels spinning, sometimes you have the wheels spinning in this direction and then in that direction, then again in this direction and then in that direction. Why is that? Does that happen? It's a classical case of aliasing. So aliasing happens there as the wheel spins. Let's say that I have this point here, and this rotates like that. So I had a certain rotation frequency and period, omega s ts. And let's say that my sampling period, ts, is at 3/4 of the actual period. So I'm going to take the next, as this has rotated, it has, that red dot will be at what point at 3/4 of the rotating period? If this was a clock, what time would it be? 9, yeah, it would be at 9, right? Because this is 3/4 of a turn. And then if I take the next point, where would it be? 6. And if I take the next point, it would be like this, and this is 1, well, this is a 0.23, and you see that I'm creating a fictitious artificial rotation like this. This is alias. Okay? Well, can I understand why I'm getting this, and can I actually understand what is the corresponding frequency for this? Bear with me so that we can do this exercise, and we can repeat the exercise here for the signal, which is easier. By doing example 3, which is on page 11 of the notes, which is a more realistic system. It's a nice example from Ostrom and Wittenmark, which refers to a process. So here we have the following thing. We have a heat exchanger here. We have feed here. And we have steam going through. And here we can have a steam trap. So the basic idea is that you have water and have steam. Okay. And you have here a valve. And this goes like this. Okay. This is not a block diagram. This is real metal, right? There's fluid here flowing. There's fluid flowing here. There's steam flowing here. There is water. There is water here. This is condensate, right? Condensed water, condensed steam rather. Water from condensed steam. Okay, now I have sensors and I measure the temperature downstream and the pressure downstream. My temperature sensor is a discrete sensor, digital sensor. Actually, I have a thermocouple, but I don't have access to the voltage, so I just look at what my computer samples. The sampling is every 2 minutes. So I have here lots of points, continue over time. And between 2 points, I have 2 minutes. Okay, so time is in minutes. As I take measurements, I observe this pattern. Here I'll try to do it for this temperature at TK essentially. So this is TK. I have this pattern which I'm going to draw approximately. I have these points here one by one. And any 2 points are, well, let me try to make it a little better. Just like this. And between these 2 peaks, I have 38 minutes. Okay. Now, I also notice that I measure the pressure downstream here. I get a signal which is continuous. I have a DP cell and I can look at the DP cell continuously actually. So I get a signal which is like this. I'm drawing this again approximately. This is time in minutes again. And these oscillations here, which are of course idealized so we can quickly understand what's going on here, are 2.11 minutes. So I am thinking I have oscillations at that frequency when I get a continuous signal. I get this oscillation from my sampled temperature. Now, I know the temperature cannot change very fast, but could it be that there is something wrong in this picture? Why could there be something wrong? Could it be that this signal here in temperature may be due to aliasing rather than being a real signal? So why am I suspecting aliasing? Well, I'm trying to understand why I'm getting these oscillations in pressure. Well, these oscillations in pressure suggest that there's something wrong with the valve here. The stem here has dead space and it doesn't fit very well, so it chatters. The valve goes up, down, up, down, up, down, up, down. And every 2 minutes, that's the reason, I mean, the pressure that I see here continuously changing with 2.11 minute period is likely due to that flutter that I see in the stem of the valve. Okay, but then again, if the valve goes up and down, up and down, up and down, up and down, I see this change in pressure, well, that should indicate that the flow rate should have the same oscillation, right? And if the flow rate has the same oscillation, the residence time of the water that goes to that heater should change accordingly, right? And if the residence time of the water in the heater changes accordingly, shouldn't I suspect that the temperature at the outlet should change at the same frequency? That would make sense. So I have a suspicion that this signal here may be due to aliasing. Well, can I test my theory? Well, what is my theory then? My theory is that it is possible that what I see here is actually not the real signal. It is possible that what the real signal T is the same oscillation signal that I have in pressure, but because I do not sample frequently enough, well, I have to do this. Let me just do this in this following way. Because oops, I erased this. So, sorry. Do it again. So, same oscillation as pressure. When I sample, and I'll copy actually the exact figure from the notes. When I sample, it's at these points where I cut this. Could it be that that period that I notice here, which is 38 minutes, is due to not sampling this frequently enough, and this same period is again 2.11 minutes for the signal. Well, let me test my theory. So my sampling period is frequency rather is what? It's 2 pi over ts, and there's an s missing here, so it's probably a typo in the notes. So it's 2 pi. How frequently? Well, what is the period of my sampling? No, 2.1 is this, the peak to peak. 2, right? So it's pi, 3.142. Well, radians per minute. All right. What is the frequency of my signal? Well, I need the largest frequency of my signal. It has only one frequency, so that one frequency is the largest frequency, which is 2 pi over T0. So 2 pi, what is the period of my signal that I'm alleging underlies all this? Yeah, this is the 2.11. So I do the number crunching, I get 2.978 with 4 significant digits. That's good enough radians per minute. All right, now my magic formula says that if I am to observe alias frequencies, those are the frequencies of this form. So K, oh, K, I forgot to mention it, K is an integer. Okay, so 0, 1, 2, 3, etc. So, I'm sorry, not 0, 1, 2, 3, etc. So as many frequencies of omega A as I can fit in here will be alias frequencies. So let's see, first of all, what would be the Nyquist frequency? Or let's just apply this directly. So for K equal, so 1, 2, 3, etc. Right. So for K equal to 1, I have omega S plus or minus omega 0. So let's do that. Omega S plus or minus omega 0. Can I fit this between 0 and omega n? Well, omega n, we said it's pi over the sampling period, which is equal to how much? 3.14. The sampling period is 2, so it's 1.67. Do you agree? Okay, so this is my Nyquist frequency here. Can I fit anything like that between 0 and 1.67? Well, let's see. Omega S, we said, is how much? 3.142. All right. If I go plus omega 0, what was omega 0? 0.978. Is that less than that? And between this, so it's okay on the left, but is it less than 1.67? No, clearly not. Okay, forget about that. Okay, let me try with the minus. Minus 0.978. The result is 0.1638 radians per minute. Is this greater than 0? Yes. How about on the right, less than 1.67? Okay, so that qualifies for an LES frequency. Now, if that is an LES frequency, I should see this LES frequency in the blue signal. So for the blue signal, I measured the period here, peak to peak. So is this frequency actually commensurate with that period? Let's see, the corresponding LES, alleged LES period would be 2 pi over omega LES, 2 pi over 0.1638. And lo and behold, you do the math and it comes to 38 minutes per cycle. Okay. So this indeed gives me very strong evidence that indeed what I observe is an LES signal. It's not the real temperature. This is actually due to not sampling fast enough. In the notes, I have a better figure. Let me copy that and actually stick it in these notes so that we can have something better for reference. So for this, I have this here, which explains what I observed here. This is a better figure so we can actually visualize this a little better. Okay, the blue dots are what I put here in blue, the continuous signal in this, and you see why we get LES. To cut to eliminate aliasing. Aliasing because signals may actually be fairly fast when you have mechanical systems, like a valve, for example, a compressor, things that have RPMs that maybe in the hundreds or thousands. Those can easily give you LDS frequencies, which is why in sensing, in taking measurements, let's say, of flow rate after a pump, because you may have all these changes in pressure downstream or flow rate downstream, to avoid aliasing, sensors may be what we call smart sensors. We said that smart sensors do lots of things to qualify as smart. Intelligent may be a better buzzword these days. So intelligent may actually be smarter than smart. I don't know, it's a buzzword. But in terms of what they do, smart sensors have capabilities. One is for calibration. They want to, sometimes they do automatic calibration to ensure that there is no bias in the measurements they take. Another property is denoising. They can remove noise. And finally, one thing that they can do is filtering of high frequency content. What is that? If I am sampling at a certain sampling period, the frequencies that I want to make sure that are contained in my signal must be up to that point. Everything above that should be cut off. So these smart sensors cut off those frequencies in a nice way from the continuous signal before it is sampled to avoid these alias frequencies. Electrical engineers have done the homework of that, and they have beautiful and powerful filters that do anything you can imagine, from maximum roll-off rate to the right phase, minimum delay. They have names for these filters, but these are things for another discussion. So we'll stop here, and rather we explain what section 7 in the notes discusses, which is a useful rule of thumb used extensively in industry. It says, if I have a process in my unit, typically I can represent that process by this Laplace domain transfer function, k e to the minus theta s tau s plus 1. This is typically my manipulated input. This is my controlled output. We have already seen lots of examples, and we know how to go back and forth, time domain to Laplace domain, etc. The idea is, if I have a signal like this, which comes from a computer over time, how frequently should I sample that signal that I get from my process? Well, what we learned in the previous chapter in frequency response methods actually can help us with that. So if we have such a process, we learned that I can create a nice diagram that provides the logarithm of the amplitude ratio. What is the amplitude ratio again? Remind me. If we throw a sine, we'll get eventually a sine of the exact same frequency, but different amplitude, right? So A sine omega t is the input. I'll get A hat sine omega t plus theta. What is the amplitude ratio for a transfer function g of s? How do I define the amplitude ratio? Wonderful. It's exactly that. In fact, so this is a definition. And there is a theorem that tells me that this amplitude ratio is equal to the magnitude of, wonderful, g of j omega. Okay. So if g of s is this thing here, then all I need here is g of j omega. So I need by g of j omega, which is the k tau j omega plus 1, the magnitude of this, times the magnitude of e to the minus j omega theta. We did this exercise last time, so this is a complex. This here is a complex number in polar form. The magnitude of a number in polar form that has a 1 in front of it. What is the magnitude of that? 1. Okay, so this 1, so this drops out. Therefore, the magnitude here, the magnitude that gives me the amplitude ratio is simply a first order system magnitude, right? And I know how this behaves if I plot log omega, log amplitude ratio rather versus log omega. There are two asymptotes, this and that. The high frequency asymptote has what slope? -1. There is a break frequency at what frequency? Yeah, excellent. Or in logarithmic if you prefer, minus log tau. And this here is, or if you prefer the amplitude ratio, also that here, this is equal to the low frequency asymptote. Yeah, well, k. Yeah, log k if you have a gain k. Amplitude, actually amplitude is absolute value of k, and the logarithm of that here. Okay, wonderful. Well, this is telling us something qualitatively now. It's not just about the numbers. It tells us that frequencies in this range, frequencies in this range here will have a magnitude which is going to be much, much smaller than the frequencies of the input signal. So you won't see the effect of these frequencies. I've explained several times that this is essentially the function of a filter. The system filters the input frequencies. The low frequencies go through. These go through with about the same amplitude. The high frequencies do not go through. Their amplitude becomes smaller and smaller. And of course, we have explained that the actual curve is something like that. So that basically says that the output signal that we have there, the output signal that we have there in the output of my system, does not contain many high frequencies compared to the low frequencies. So it's safe to say that, well, there is roughly an omega 0 frequency here, which is the highest frequency. And if I sample, I know from the Nyquist theorem that the sampling frequency must be greater than twice the highest frequency of my signal. Okay, so what is a good estimate for this omega 0? Well, I know this, which I will call the break frequency. The frequency, well, not this actually, this is, sorry, logarithm. This is the logarithm, the break frequency. This thing here is the break frequency, which is 1 over tau. Okay, so this break frequency, which is 1 over tau, is here at this point. Well, if I want to be here, I can go perhaps a little bit to the right by how much? Well, 1 decade. If I go in this direction 1 decade, then the amplitude ratio is going to drop by another decade because the slope here is -1, as we have said, right? So omega 0 then is about order of magnitude, let's say 10 times omega b, right? And omega b is 1 over tau, so ten times omega b, which is 10 times over tau. So this omega 0, therefore my omega s must be greater than 2 times 10 divided by tau, so it's about 20 over tau, which means my sampling period, which is 2 pi over omega s, must be less than 2 pi over omega s, which is 20 over tau, and this is pi over 10, so it's, how much is that? It's about pi over 10, it's about 0.3 tau, right? So this says roughly that if my sampling period is less than 0.3 tau, I'm going to be in good shape. And that's where this rule of thumb comes from. It doesn't come from experience alone. There's well developed theory which is rigorous, and it's guaranteed to give you pretty good results if you apply that. In terms of intuition, actually, we know how we can see the dynamics of a first order system such as this. We know that if we make a step change to the input u, the output is going to respond roughly something like here, something like this. Sorry, yeah. This is my y of t, and we know that we can approximate this by first order plus time delay. So if you have this to be here, the range over which you have almost reached the steady state, how many points would you? Yeah, one would say 5, 6, 10 points visually are good enough, right? Of course, in theory, just two would, actually just 3 points to this, just a middle point, and this point would be good enough, but it's not good for other practical purposes. So this is where this rule of thumb comes from. Now, in the next lecture, we're going to see how the computer looks at the process. So far, we have seen how we can look at the process and understand how to sample the process, describe it to the computer, send samples to the computer, and let the computer do some number crunching. The computer doesn't understand the process in continuous time. The computer understands the process in discrete time. For example, if we have a differential equation dx over dt equals f of x of t and u of t, so this is my mv, this is x is my cv, my control variable. That's what we understand, that's what the process understands. The computer doesn't understand this. We can explain this to the computer. The simplest way is by using finite differences, and we already mentioned that in a previous lecture. So basically we say if we approximate that derivative, which is the derivative of this function x of t versus t at time tk, we look at the next point tk plus 1, which is here, and we approximate this derivative, which is dx over dt at tk, or otherwise x prime at tk is the same thing. If we approximate it by a finite divided difference, which is this difference by that difference, we get that the derivative dx over dt at tk is approximately equal to this, which is this point, which is x at tk plus 1. So let me just say xk plus 1 minus this, which is xk. So it's the difference between these two, divided by the difference between these two, which is delta t. And this is approximately equal to the right-hand side at tk. So xk uk. This is a quick and dirty way. Quick because it takes very little calculation. Dirty because it involves some approximation. But nevertheless, it's good enough to give us what is now known as not a differential, but a difference equation. It says the next value of my process CV is a function of previous data, the previous time step. Simple, nice approximation. There are others, which we're going to see in more detail, so we can understand how this works. So next time, we're going to see examples of how we can discretize systems, what to do with discrete time system, how to design controllers, and better yet, this will give us some inspiration for how we actually develop such systems, such equations. It will turn out that you can write this as simply equal to AXK plus BUK, and get this A and B just from data, doing regression. That's an experiment, again, that people do all the time. It's the same experiment like this, but you may use this idea to fit these data to this, to fit the equation to the data you collect in this experiment. So I'll stop here. We'll finish our theoretical toolbox next time. I'll see some designs and some simulations actually to visualize it. I'll stop here and continue with the next.